37, 36. Okay, so let's see. Oh, okay. So I don't want you guys to forget transformations. And we talked really quickly about the fact that I could take this function, which is one of the functions we just need to know what it looks like. So it's very, very, very remarkably roughly like that, right? It's one of the simplest forms of a hyperbola. So I could move it around. And we did one the other day where if I put a 1 over x minus 1, what would happen here? So what exactly moves? Yeah, exactly. Cool. So this vertical asymptote would move over to 1, and then the shape would basically stay the same. And the only time that this horizontal asymptote would move is if I had a shift up or down, right? If I have an infinitely long pipe and I shift it over 1, it's still infinitely long in both directions. Doesn't care. Oh no. So on this number 36, they give me several things happening. So what kind of shift is that?
So right 2.
Yep, right 2. And what happens here?
It goes up 1. Doesn't it? It's an
It flips over the...
Good. It's a reflection. Yeah, across the x-axis. I like it because it takes all of those values and makes them the opposite of what they would be. So it takes the y values and makes it the opposite. So it's a flip across the x-axis. Good. It's a stretch. So if I have f of x equals 1 over x, g of x equals 2 over x is twice f. So it just takes all the values and doubles them, right? Okay, maybe. So now you just have to apply those transformations to 1 over x, the black line. I'll let you guys try that. Did you try that yet, or did you not know what they wanted to have happen? Okay. So they want you to start with the base function of 1 over x, and then just apply the transformations to it. Yeah. Cool. Yeah. In that same section, I guess?
Yeah.
Okay. Oh, yeah. I like this. Blah, 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 blah. Does any budding photographers out there? Anybody does? Yeah? So you familiar with this equation at all? Possibly not. So this is the physics behind focal length. Yeah. And actually, we don't care about this. This is the algebraic equation behind focal length. So what they're asking me to do here, suppose the camera has a 55 millimeter lens, which means the focal length is 55 millimeters. Express y as a function of x, so you just have to solve for y. Right, so that's part A, is just solve for y. So which part of this problem gave you trouble? Yeah, what does x represent in this problem? Look at the picture. Yeah, the distance between what and what? Yeah, the actual physical object, in this case a person, and the lens, right? So you've got your camera sitting in front of you, and I'm going to take a picture of you. So x would be how far the camera is away from Ryan, right? So x is that physical distance. So what part B says is what happens to y as the object moves far away from the lens. So what does that mean when I say as the object moves far away? I'm going to let what happen to x go to infinity. So part B says what happens to y as x goes to infinity. Now, so you got to get part A done first before you can hope to do anything with part B. Okay, maybe. So how do you do part A? Maybe we should start with that. So if I have this function, how do you solve for y? I like it. So 1 over y equals 1 over 55 minus 1 over x.
Multiplied by y.
Now the horrible thing to do is to try to tell me that y equals 55 minus x. So if you're thinking that, sponge that right out of your brain. Right? Now where would somebody get that? Why would somebody believe this is true? Because they, oh, if I just turn that over, I can just turn these over. It's not that easy. If you turn this side over, you'd have to turn this whole side. It would be 1 over 1/55 minus 1 over x, which is horrendous. Yeah, so you get a common denominator and make it a single fraction, and then it's easy to flip. I like it. So then we get 1 over y equals, what does this guy need? X. What's this guy need? 55. So we get x minus 55 over 55x. So y must be...
There. Flip it.
Yeah, do the same thing to both sides. So if I flip that side, I better flip that side. So now it's easy. Now part B is simple. If I let x go to infinity, that is also known as the what of this graph. What kind of asymptote? So let x get really big. Horizontal asymptote, right? So, and what situation am I in? Now that I've got the form of it, it's an easy question. It's my hope. What situation am I in for horizontal asymptote?
The same.
Same degree, so
55.
55. There you go. So as the person moves far away, the image will focus at 55 millimeters, which is kind of cool. So I don't know if you guys have ever done that. Have you ever had a lens and you face it towards the outside, and you're in a dark room, and you move it until you get the image on the... If you've never done that, find a lens somewhere, just do it. It's kind of neat, because you get an image of outside that's upside down, and like, ooh, neato, right? Or whatever you want to say that sounds better, right? Anyway, so part C says, what happens as the object moves close to the lens? So what does that mean? What do I allow to have happen mathematically that relates to the physical? Let the object get close to the lens. Let x... Negative infinity would mean you go through the lens, which is a totally different... You have to be probably intoxicated to believe that it's happened. So as x goes to what? The distance from the lens, I want it to go to 0 to let the thing get close. As x goes to 0, what's happening to my y?
Get smaller?
Goes to 0. Right? If x goes to 0, you get 0 over negative whatever. Okay. Alright, enough of that. What gets really neat, and what's beyond the math of this problem, is if you'll notice, the image distance from the lens becomes negative if you're within the focal length. Let me say it again. If you're within the focal length, you get a negative image distance, which means the image is created on the same side as you are, which is actually called a, what's the name of it, Jeff? A real image. I think it's just called a real image. There's a really cool YouTube thing about a mirror they have set up, this giant mirror that you stand close to, and it creates a real image, and the weird stuff that happens with real images. If you're at all interested, you can Google that later. If you'll forget about it, it's okay. You still can do the math. Yeah.
So that notation is the same as saying f of 0.
No, I want you to be real careful. This notation is not the same as just saying this. In this case, I could just plug a 0 in, right? But I can never plug an infinity in. You just can't. I know some people do, but you can't. You have to let x get really big, and this is let x get really small. So it's a slightly bigger idea. You don't actually ever get to 0, you just get close to 0. All right, so if you take calculus, again, your whole first 2 weeks will be trying to understand what I just said. You don't get there, you get really close to there, because something freaky might happen there. Yeah. Okay, maybe. Okay. I continue to depress some of you guys. I'm sorry. 87?
Yeah, same.
Oh. What's the matter? You alright?
Yeah, no, I just got kicked in the jaw. No, this weekend.
That was okay. That was exceptional ninja skills. I would not have angered this person, whoever kicked you. It reminds me of
You should have seen the other girl.
what was that movie? Chris Rock, Jackie Chan. Who just kicked me? Rush Hour. That's the one. One of you guys just kicked me. All right, so 87 is another physics thing. I don't think that the Doppler effect. So this is when imitate a car going by you. And then what happens here? Nobody wants to do it. Right? So that's the Doppler effect. As it's coming towards me, the waves of sound get compressed because it's coming towards me, so it sounds higher. And as it's going away from me, the waves of sound get further apart, so it sounds lower frequency.
Speaking of waves, did you hear that they created solid light?
Solid light.
Because you know how light is normally measured in waves. They created solid, so
Well,
it's not waves anymore.
light is both solid and wave. But anyway, I'll have to look it up. I'll have to see what you're talking about. So 87 says, Doppler effect, the observed pitch P is a function of the speed of the train. So the pitch that you hear these are S's here, trying to be so. P naught is the actual pitch, and the speed of sound in air is S naught. This is the actual sound, the actual pitch. Not pitch, Jeff, pitch. In my head it said pitch, and it started writing. This is the speed of sound in air. All right. So, whenever they give you a problem like this, you've got a function with all these letters in it, the first thing you got to do is figure out what the hell each letter means. Just keep that in mind. Right? So what we had to do over here, we had to figure out, if they said I was moving far away, I had to figure out which variable was that related to before I could do anything mathematically. Right? So you have to know what the variables represent. So everything with a little O on it is set. I can change my velocity. And the faster I go, the higher the pitch is going to sound, and so forth. So they want you just to investigate that. They say, suppose that a train has a whistle pitched at 440 hertz. So say this is 440 hertz. Graph the function using a graphing device. All right, so you just got to plot this bad boy. Make y1 equal to 440. Now they tell you the speed of sound in air. 332 meters per second. So that's what you would put in your calculator, right? The true variable in this whole thing, you can see it right there, is the velocity. That's what this function is letting change. So the pitch is a function of the velocity. If it's coming really fast at me, it's going to go, right? Right? Does that kind of thing? So you just got to throw this in the calculator, and it says, how can the vertical asymptote of this function be interpreted physically? So I'm going to leave that one to you. I did the last one. This is number 87. But at least it got you to this point if you weren't able to figure out how to put it in the graphing calculator. Take a look at it. What will the vertical asymptote be? 332. Right? 332. So it's got something to do with the speed of sound. So I'm going to stop right there. You just got to think about what that might mean physically. This is the velocity the train is traveling at. So think about a jet. What happens to a jet when it hits the speed of sound and goes beyond? Sonic boom, right? Mach 1, Mach 2, Mach 3. Yeah, that's going to be like Back to the Future train, right? Okay, so anything else? That's as far as I'm going to go on that one. Anything else from homework? Okay, all right. So let's get into chapter 4 in all the time we have left. Let's see. Now, I'm going to say this, but I want you guys to definitely slow me down if I hit something that's kind of weird. Most of this should be reviewed. You should have all, hopefully, talked about exponential functions. You should have all, hopefully, talked about logarithms before. And maybe some of us have talked about it, but we really hated them, and we're not sure why they exist and what the hell. And why are they called logs? What the hell's wrong? Yeah.
That's me.
Okay.
That's a shaky drive.
Of course, since I moved to California, logarithms have a lot more to do with living in California. Does anybody know how?
Because they experience exponential growth and stuff.
What happens in California that doesn't happen as often in another state? Earthquakes. So, of course, the Richter scale is based on logarithms. So if you have an earthquake of magnitude 4.0 versus 4.1, it's a much larger increase in energy than it sounds like to us because it's a logarithmic scale. And the logarithms kind of like understate the changes in things. Decibels are also measured using logarithms, just to kind of bring it down to a scale I can kind of relate to. So you all heard of decibels before, right? Okay, good. What was that first earthquake? All right. So exponential functions. We've if I was teaching my 110 classes, I tell them, we put that variable underneath a number, we put it next to a number, we put the variable with a number in the exponent, we've put the variable under a root. We've done all these things with it, and the only thing we haven't done yet is put the variable itself up here.
Oh God.
I don't remember.
Because I saw 210.
Well, you got to go back and look at the videos, because we did. We totally did.
You deleted them already.
No, I haven't. They exist on YouTube forever. All the way back to the first one I ever did.
You just gotta go to the black internet.
So when you first hit a new function, this is not new to most of us, shouldn't be. When you first hit a new function, you investigate it by making a table of values. Now, exponential functions, exponential growth, exponential decay, if I have money compounding continuously, if I have plutonium releasing radioactivity and becoming less and less radioactive over time, I have to model that using exponential functions. So population growth, put a couple rabbits in a room, make sure they're different sexes, give them some money, give them some money, give them some food, let them go at it. You can measure the population growth using exponential functions. So, let's put some stuff in there. When I have a function that I don't know, I should put some negatives and some positives in there and take a look at what's going on. Bless you. So what do I get when I put a negative 1 in there? 1/2, good. I don't think I heard a negative 2, thank God. So a 2 to a negative power just flips it, right? Negative powers just flip.
Yeah.
Of course, when I put a 0 in there, I get 1, thank God. And then when I put a 1 in there, 2. And just to kind of, let's put 2 and negative 2 in there. 2 squared is crazy. Negative 2 to the negative 2 is 1/4. I love it. So try to graph that real quick. Realizing that what happens if I let x go to negative infinity? To what? To 0. Good, because the top is always going to be 1. If it was 2 to the negative 1,000th, 2 to the negative 1,000th power would be 1 over 2 to the 1,000th power, which is really stupid small, but it's not equal to 0, is it? So you can tack on as many zeros as you want to onto that, what I just did, and it's going to be the same story. Every time you put another 0 on, it's just smaller. But it doesn't equal 0. So of course that is an asymptote. Right, so it gets really, really close to 0 on the negative side of things, as x gets really big negative. Of course, as x gets really big positive, this bad boy is just going to grow. So if you're watching a horror movie and they say the monster is growing exponentially, or the virus is spreading exponentially, that's what it means. It goes, and they go, whoa, and it just goes crazy. And the whole Earth, and then the moon, and then who knows.
Sounds kind of like 110 again.
Thank you. You should remind other people.
It doesn't sound like one. He didn't talk about
He used that same
He didn't talk about monsters.
Yeah, he did.
Sure did.
It was hard out there.
Anyway, let's not relive the past.
It was gremlins.
So what does this thing look like if you graph this thing? So I got 0 is 1, 1 is 2, 2 is 4. Negative 1 goes to 1/2. Negative 2 goes to 1/4. So it looks like that. Of course, this just keeps going.
Oops.
Now you can't erase.
That's all right. Yeah, OCD teachers going to go crazy about that, but too bad. And that is the basic look for any number I put here. But if I would have put a 3 here, what would have been different?
How fast is it?
And what would have been the same? What would have been exactly the same?
The asymptote.
Well, the asymptote, I think.
The y-intercept.
Yes, that y-intercept, no matter what I make it, it's something to the 0 power is 1. Except for 0. 0 to the 0 power is freaky. Right, so anything I do, so if I would have made it 3, it would have been 1 would have gone to 3, negative 1 would have gone to 1/3, so it would have been a little bit faster rising and a little bit quicker dying in the backside. Okay. Cool. Not too bad. So this is, again, it should be review.
Wait, what is 0 to the 0 power?
Error.
So 1/0 we call undefined. Things like 0/0 or 0 to the 0, I've used this word once before at least, it's worse than undefined, it's indeterminate.
So we don't know.
Does math not know
So-
what it is, or it's...
No, you can actually calculate, it's depending on where these come from. So, I mean, if I let, what do you want to say, Jeff? What can I put down here? Well, we're not there yet. Shit, I can't use that. All right, so it's depending on where these come from, calculus can figure it out. So the whole problem with this is, I don't know. This normally comes from what for us? Where would this come from? Letting x get really big or something, right? Or letting x get really small in this case. So calculus is all about how quickly things are moving. So it would totally depend on which one's going to 0 faster, the top or the bottom. It's a lot like horizontal asymptotes. Is the top or bottom going to infinity faster? Or are they going at the same rate? That's a little bit beyond what we need to talk about right now. So, but she asked, and I always like when people ask. So now we can do, I want you to realize something though. So square root of 3, which is like 1.7 something or other. I know what the 2 to the square root of 3 is. I can just look at the graph and see what it is. But 2 to the square root of 3, can you, like 2 to the 1/3, how could I rewrite 2 to the 1/3?
Cube root of 2.
Cube root of 2. How can you write 2 to the square root of 3? You really can't. So the way you do it is, let me try something else. 2 to the pi. 2 to the pi, well, pi is about 3.14, right? So it's not equal to this, is it? No. But this I can write as a root, believe it or not. This is 3 and 1400ths. So it's 314 over 100. So it's the 100th root of 2 to the 314 power. Holy shit. Now, don't freak out. We can't. I'm not going to make you do this by hand or something. That's the only reason you should freak out right now. That's completely doable. 100th root of 2 is disgusting, but it's a number, right? Raise that to the 314 power, a number. So what I would do is I would just keep going, add another term, add another term, add another term, and I would just look at the limit as I let all those digits of pi show up. Because every time I stop, it's rational. I can make it into a root. You guys semi with me? I know what 7 to the 1/4, I can write that. I can figure that out. What is 7 to the 1/4? 4 through to 7. I can do that. I can put that in the calculator, right? I can figure out what that is. I can estimate it. But when I have a power that's not rational, I can't rewrite it as a root. Why were we able to rewrite this as a root? Because I know what the bottom is. That's the root, right?
So you're saying because it's non-specific, you can't technically
Since
write
it doesn't end.
Okay.
If I have a number that ends, I can write that as a fraction, and then I can rewrite that as a root. But if I just kind of don't go forever, go a little bit, go a little bit, go a little bit, and then see what number it's approaching as I put more and more digits of pi, I say the answer is the limit of putting all the digits of pi in there. You guys semi with yes?
So if you did 22 over 7, still, all that was still pi?
Yeah, because 22 over 7 is not equal to pi. I want to make sure you understand that. 22 over 7 is a decent approximation to pi. Right? But if you ever found a fraction that equaled pi, you should call any math person up and immediately reap tons of rewards of money and fame. Right? Because that just hasn't been found to be true.
You might be murdered.
Could be, yeah, considering the descendant of Cardano might come get you.
And the story in the calculus book, don't you?
Yeah, I know, you'll get a little thing on the side where they have the people on the side. Okay. Now, I desperately, you guys should know me by now. I'm not going to make you do anything with what I just said. I want you to realize that we can now do 2 to any real number. Even if I can't immediately rewrite 2 to the pi as some root, I can't. 2 to the pi is still equal to something. If you did it in your calculator, 2 to the pi,
8.8249.
and the calculator does its best it can, right? The screen's only so big, but we know it goes forever. It is a number. So that's all I want you to realize, is it doesn't have to be rational. It can be irrational now, the power. And that's why I was able to make a solid line. Every possible real number has an output. All right, I made way too big of a deal out of that. But that's actually some little thing that people don't realize what we just done. Blah, 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 blah. So what we're going to do now is every time we learn a new function, one of the first things we're going to have, so we know what 2 to the x looks like. So what would that look like?
Right 3 up 1.
Yeah, so you'd have to, what would the shifts be?
Right 3.
Right 3?
Up 1.
No.
And
Flip it and stretch.
Yeah, up 1's the last thing you do, right?
okay, go
Flip over,
x-axis.
good, x-axis. I love it. So I really want you to realize that transformations are actually really useful, and that's why they're never going to quite go away, because they're always there. If I know the base function and I just have to move it a little bit, that's the quickest way to graph the damn thing. Yeah?
What if the -2 were in parentheses?
Oh, I see. So what if it was this? Like that?
Yeah.
Now that gets freaky. Because I want you to realize something. I like that you brought that up. Because what's -2 to the first power?
-2.
What's -2 to the second power?
-4. Oh.
4? That's better. It's -2 cubed. It's -2 to the fourth power.
16.
So if you try to graph this thing, it's like constantly bouncing back and forth, isn't it? Because the output is positive, and then it's negative, and then it's positive, and then it's negative. That is a freaky looking dude. Right, so we're not going to worry about that.
Just yet.
Yeah.
Well, yeah. All right, so I'll worry about that. It's a little freaky. This is what's called an alternating. You can tell. You can see why we call it that. We call it an alternating function, alternating series, really.
So we'll just do it 2.5.
Exactly. We're going to stop talking about it right now, because that would lead into what I'm going to talk about Calcs 2 students next week. So we're not going to go there quite yet. Okay. So all you have to worry about in this homework is some basic stuff with exponentials, graphing it, transforming it, plotting some functions, plugging in some stuff. Yep, and that's it.
I won't grab it.
What's
I
up?
won't graph it.
Yeah, this guy? No. Hell no.
It's like, nope.
And what I'm waiting for is, now the one I definitely wouldn't touch, that you guys might not even think about, is what the hell is this?
Yep.
What?
That was on my junior year of college math proficiency exam. We had to analyze this function. And the guy who made the problem was just standing outside the door just laughing. It was great. Yeah, no, we're not going to talk about that. I mean, it's neat. It's neat. I really want you to understand. It's not just, obviously I would like that. Obviously I would play with that because I'm a geek. I'm a little biased. But it's just weird to stop and think, what the hell, what would be wrong with this function? If x is negative, like negative 1/2 to the negative 1/2, what's wrong with that?
You have to flip it.
What is the 1/2 power?
It's
It's
a
a
square.
Square root of a
Negative.
negative number, so it wouldn't be real. So the graphing calculator would freak out. But right next to that is negative 1/3 to the negative 1/3. Can a cube root handle negative?
Yes.
Yes. So that's even worse than this dude.
I know, it graphed it.
Well, it graphed part of
But
it.
not on the backside, right?
Yeah, no.
On the negative part, it didn't graph a damn thing, even though some answers work. Positive side's easy. Everything's positive. Who cares?
Oh, yeah.
It'll grow really good.
Yeah.
All right. No, about 2/3 of you right now are probably like, what am I going to have to do, man? But I love these questions that I try to point out when they go further than what is required of you. But at the same time, I want you to realize there's a lot of room to play in math, especially if you're going to calculus. You're going to have to get really used. In fact, later this semester, we're going to have to get used to being able to play with expressions, especially when we get to trigonometry. Oh yeah.
So this was 4-1 we've been talking about.
Yeah. So last thing we'll do today is talk real quick about 4-2.
Is that long?
So there's a number. We had this graph up here earlier for 2 to the x.
Right.
It was like this here. This is 2 to the x. So like that. And then I had 3 to the x right next to that, right?
Yeah.
I wanted to point out that it would grow faster
It has the same intercept.
and it would shrink faster. Right in between 2 and 3, there is a base that is really good and really weird where it kind of pops out from. And it's a number akin to pi, 3.1415, blah, blah, blah. So the ancients, I love that. They took a circle and they divided their circumference by the diameter and they got this number pi. So they gave it a symbol. They thought it was from God. They thought it was divine. This is the same kind of idea. There's a special number right in the middle somewhere between 2 and 3 that models population growth and decay and all that kind of stuff really well. Let me show you somewhere else it comes from. 1 over x, right? So that looks like this and down there. From 1 to some number. And then look, when I draw that, isn't this like an area there? So what's really neat is that's what calculus does, and we don't have to worry about calculus, but calculus finds areas underneath curves. That, there's no geometry formula for the area of that shape, right? There's a geometry formula for rectangle, length times width, triangle. There's none for curvy dude that's part of this line. You with me? But what's really neat is how far out do you have to go until this area equals 1 is the number I'm talking about. And I might as well tell you, the number I'm talking about is E. 2.71828, blah, blah, blah. That's as far as I know. All right. I don't want to memorize 500 digits of anything. So that's another place where it comes, and then the last place it comes from, or another place it comes from. I want you just to think about this for a second. Just ponder that.
Is that N or H?
That's N. Now what's going on the inside? When N gets really, really big, what's happening? Yeah, this piece goes to 0, so the inside goes to 1. And what's 1 to any power?
One.
Depends
1.
on- Oh, yeah.
Does the inside ever actually get to 1?
No.
No. But it makes sense. It's getting really close to 1, and 1 to any power is 1. But what's happening to the power?
It's increasing.
It's getting really big, right? So do me a favor. Do 1.01 to the 100th power. Yeah, so what do you got now? So N is 100. we'll get 1.01 to the 100th power. You guys see that? If I do n 100, 1 plus 100th
Yeah.
to the 100th power, and what do you get?
2.0.
So now if I put 1,000 in there, of course, I'll get even closer to E. No, something wrong there.
2.71692.
Yeah, I'm getting closer and closer to this dude, right? So the limit of this, which is weird, it's got two competing things. The inside's going to 1, so 1 to any power should be 1. The power's going to infinity, so anything to the infinite power would be infinity. So they fight and they come out to E. They come out to this exactly. I'm sorry, but each of these three is neat. Hopefully a little bit. At least a few of you guys are humoring me like that. So now we have E is an acceptable, any real number except 0 could be the base of something. And the negative numbers we want to stay away from normally. But E is special. And you see E everywhere. And once you get to calculus, E will just be a part of what you do.
Kind of like
Yeah.
pi.
Elise, are you good?
Oh, never mind.
Okay. So they ask you a lot of the same questions in section 4.2, just dealing with the base of E, not a base of 2 or 3. Okay. So I think that's plenty for today. So next time we'll get into the inverse function for exponentials. Logs, yeah, exactly.
So for this, all I have to do